In this lecture, we are going to discuss about a particular theorem that is known as Lagrange's theorem. Now, this theorem can be proved by two methods. The one method is by the use of equivalence relation, which we have discussed in our earlier lecture, and another method is straightforward method. But in this lecture, we will prove the Lagrange's theorem by the method of equivalence. Now, I request the viewers to go through the lectures of equivalence relation and classes, which was delivered just earlier to this lecture. So, I am just highlighting the major points of that lecture again. So, the equivalence relation is written in this way, that is x equivalent to y, and if x is equivalent to y belonging to S, x and y are the elements which belongs to S. So, it obeys some properties, that is, for example, reflexivity, x is equivalent to x, symmetry, x equivalent to y implies y is equivalent to x, and transitivity, that is x is equivalent to y and y is equivalent to z implies x is equivalent to z. So, these properties are hold for equivalence relation. And another important thing is that equivalence relation on S, this is very important, that is equivalence relation on S, S is a particular set, divides up S into classes Ci. So, equivalence relation S divides the S into classes Ci. Classes Ci are the subsets. But how it divides? So that x and y belong to the same class if and only if x is equivalent to y. So, x and y are the two elements, they belong to the same class if and only if x is equivalent to y. And every element w of S belong to exactly one class. So, S contains several elements, and every element w is any element, but we are saying in this way, that is every element w of S belongs to exactly one class. So, this is the major thing of the concept behind the equivalence relation and the classes. And other thing is like this, two different subsets Sx and Sy can have no element in common, and the collection of all the classes Ci is a partition of S. So, actually these classes are partitioning S, and that is every element in S belong to one and only one of the classes. So, these are the major concepts of the equivalence relation and the classes. Now, we take as the definition of equivalence is that given x and y belonging to G, that is x is equivalent to y if x inverse y belongs to H. So, we have to listen this sentence very carefully, that is x and y they belong to G. Now, x is equivalent to y, so this means that is x inverse y belongs to H. This is actually the definition of x is equivalent to y. But why this definition holds, that we will explain now. Now, x inverse y belongs to H is similar to saying that y is equal to x into Hi, because x inverse y is content in H. So, you take any element Hi. So, x inverse y as it belongs to H, so y that is equal to x into Hi for some element Hi belonging to H. So, this is equivalent. And technically x and y are said to be left congruent with respect to H. This is a technical terminology. So, why we are writing in this way, that is y is equal to x into Hi, that is termed as x and y are said to be left congruent with respect to H. Now, this definition, that is x inverse y belongs to H or y is equal to x Hi, this is as per accordance with the equivalence relation. Why? Because you see that reflexivity x equivalent to x, it holds, because you see that is x inverse x. If you write x inverse x, then it will be I. So I belongs to any subgroup. So we are saying that is x inverse y belongs to H. So x inverse x is equal to I. So that will belong to any subgroup. Next, the symmetry property, that is x equivalent to y, implies that x inverse y belongs to H. X equivalent to y implies that x inverse y belongs to H, and so therefore does its inverse also. It means that as x inverse y belongs to H and H is a group, so by the property of the group, the inverse of x inverse y, that means inverse of x inverse y is y inverse x. So y inverse x also belong to the group H. And from the definition, we are defining in this way that if x inverse y belongs to H, then x is equivalent to y. So similarly, we can say that if y inverse x belong to H, then y should be equivalent to x. Next, the transitivity relation. For example, x is equivalent to y and y is equivalent to z, imply that from the definition we have already given that is definition is x inverse y belongs to H when x is equivalent to y. Now if x is equivalent to y, then x inverse y belong to the group H. When y is equivalent to z, then y inverse z belong to H. And as they are two group elements for the group H, I mean that is x inverse y and y inverse z, these two elements are the group elements of H. So as per the rules of the group, product of these two elements will also be contained in H. So let us find the product. X inverse y into y inverse z means x inverse z. So x inverse z is also an element of H, and as x inverse z is an element of H, so from the definition x is equivalent to z. So this relation follows from the definition. That means the definition we have provided is correct. Now as we have discussed the earlier lecture, that is about equivalence relation and classes. So equivalence relation divides the S into classes, and these classes are disjoint or non-overlapping classes. For this particular equivalence relation, the classes are called the left cosets of H. So these particular classes are known as left cosets of H. Thus each element of G is in one and only one left coset of H. So if you consider each of the element of G, they must be contained one and only one left coset of H. The left coset containing any particular x is usually written as x into H. So if some of the coset contains x, then that particular coset is usually written as x into H, and denotes the set of elements of the form x into Hi. So this particular set denotes the set of elements of the form x into Hi, and one of the element is x itself. Why? Because H contains the identity element. So if H contains the identity element, so for a particular value of I, Hi will be I. So x into I is equal to x. So x will be it's one of the elements, and this capital H, it must contain a small h number of different elements. The element must be different. Since if did not and two elements were equal, then we could write that is x into Hi is equal to x into Hj, as two elements are equal, and by applying the cancellation law we can deduce that Hi is equal to Hj. But if Hi is equal to Hj, then what will happen? Then H will contain fewer than small h number of elements, because we have already assumed that capital H contains small h number of different elements. So it contains small h number of different elements, but here we are showing that H contains fewer than small h number of elements. Why? Because Hi is equal to Hj. So this contradicts our assumption, and so what we say, that is it must contain small h number of different elements and no two elements will be equal. From our general results about equivalence relation, it now follows that the left cosets of H are a partition of G into a number of sets, each containing small h members. So from the concept of equivalence relation and classes that we have discussed earlier, so what we are seeing that the group G has been partitioned. Group G has been partitioned into different left cosets of capital H, and each of the coset H contains small h number of elements. Since there are small g members of capital G and each must be in just one of the sets, each of the member must be in any of the sets, it follows that small g is a multiple of H. This concludes the proof of the Lagrange's theorem. The number of left cosets of capital H in G is known as the index of capital H in G. So this is known as the index of capital H in G and is written as G colon H. Numerically, the index is written in this way, that is G by H. So this is what about the Lagrange's theorem, and we have proved it by using the concept of equivalence relation and classes. For further understanding, I request the viewers to go through the textbook of mathematical methods for physics and engineering by Riley, Hobson and Benz, and thank you for listening the lecture.